This slide reports a quantum example using a 50-qubit processor to solve a scenario with 25 cranes and 100 tasks across 8 vessels. The search space is about 2 to the power of 50, roughly 10 to the power of 15 configurations. Reported outcome: makespan improves from 18 hours under a classical heuristic to 14.2 hours under the quantum solution. The reported advantage is strongest in highly constrained cases where classical methods get trapped in local optima, with reported solution quality improvements of 15 to 25%. These questions reinforce Tier 1 modeling. You build the full integer programming model for 3 cranes, 2 vessels, and 8 time periods, including a clearance distance of 2 position units. You also derive non-crossing constraints for 4 cranes and 5 bay positions under an 8-meter clearance distance, and extend the objective to include weighted completion time, idle time, and delay penalties. These questions focus on applying the EAC-SPT heuristic step by step and computing makespan and utilization. You also compare shortest processing time first, longest processing time first, and earliest due date first on an 8-task dataset. These questions ask you to design chromosome encoding and operators for a 3-crane, 8-task instance and compute a fitness function. You also propose simulated annealing parameters for 20 tasks and 5 cranes and estimate how many iterations are needed to explore 1% of the assignment space. These questions focus on reinforcement learning setup. You define a state and action space for 6 cranes and up to 4 vessels, then design a deep queue network with input length 48 and output action space size 100. You also analyze a learning curve from reward minus 150 to plus 60 over 1,000 episodes, and predict how many additional episodes would be needed to reach reward 100. These questions focus on digital twin data flow. You design real-time synchronization and compute requirements for simulating 10,000 container movements per day across integrated systems. Operationally, the point suggestion is that Quay decisions propagate to yard and transport decisions, so the twin must keep the whole system consistent. These questions ask you to design an auction mechanism for crane agents bidding on tasks. You define bidding strategies, winner determination rules, and estimate efficiency relative to centralized planning when agents have private cost information. These questions ask you to formulate a quadratic, unconstrained binary optimization matrix for a 3-crane, 6-task instance and design a 2-layer quantum approximate optimization circuit. You estimate qubits, circuit depth, and discuss when quantum advantage might appear as cranes and task scale. To close, remember that assignment and scheduling must be integrated because rail and clearance constraints couple space and time. Integer programming gives a complete specification and a correctness baseline. Heuristics provide fast, feasible schedules. Genetic algorithms improve makespan and utilization with feasibility-preserving operators. Reinforcement learning learns dynamic policies that adapt to stochastic arrivals. Digital twins connect Quay decisions to berth, yard, and transport impacts. Quantum approximate optimization is a potential path for highly constrained, large-scale instances.